In this lecture, we will cover laboratory measurements, chapters 3 and chapters 4. So different parts of the world use different methods for measurements. The United States customary system is actually based on the English system of measurement, which draws from the Greek and Roman system. These measurements are not consistent, so it can lead to some confusion among the different systems, since every system, different places throughout the world have different systems. So the metric system was developed to kind of standardize and reduce those inconsistencies, and this is based on fixed standards and uniform scales of 10. And this was developed in France in around the 1790s, and it uses three basic measurements for length, mass, and volume. So for length, we use the metric system. For mass, we use grams, and for volume, liters. And if you want to kind of see how this is done through conversions of these different units, then you can refer to Table 3.2 of your textbook. With the metric system, you have different prefixes that define whether that measurement is actually larger or smaller than that basic unit. And then the conversions are very simple to do. It's just a matter of knowing what each of those abbreviations means for that measurement. And you use basic ratio and proportion calculations to do those conversions. And so unit conversions will actually allow you to convert from one form to another using various conversion methods. And there are a couple of ways that you can do this with long math, and then a more simple way is just learning what each of those abbreviation means and moving those decimal places. And so here in this example, what we use a lot in the laboratory is microliters or milliliters. And so if we were to have 1,000 microliters and we move that decimal 3 places, 1, 2, 3, then that would give us the 1 ml. And then if we keep moving that decimal 3 more places, then that would make that 0.001 liters. So let's just say, for example, that your procedure calls for 0.25 mLs. Well, we already know that 0.25 mLs would be basically 1/4 of a full ml. And if we do that conversion and move that decimal 3 places, then that would give us 250 microliters. And so instead of trying to find a pipette, which, some of your pipettes may be specific, they may say how far that they will measure. It may be just one single measurement that they will perform. But if you knew that you don't have a pipette that says 0.25 mLs, then you would need to do that conversion and use a pipette that you could adjust to 250 microliters. So once we start looking at some of the different analytes that we measure in the clinical laboratory, you'll start seeing some more of these figures, and you'll understand how most of these are measured. When we're looking for that particular analyte, we're looking for how much of it is in that sample, in that volume of the sample that's being tested. And so it may be a measurement, for example, that's measured in milligrams per deciliter or possibly nanograms per milliliter. However, in hematology, white blood cells were originally kind of measured based on the cubic millimeters. And then now most of the machines will measure those based on units of liters per the whole blood. So how much is in that whole blood sample with everything in it? And that would be in that purple EDTA tube. The MCV is measured in femtoliters. And the metric term micro it can be abbreviated as MC in different areas of the healthcare system. So for example, medications are often measured in MCG, and that would be the micrograms for that particular drug. However, in the laboratory, we do use the Greek symbol for micro, and so we would measure something in micrograms versus whereas pharmaceuticals are more MCG. Now, we're working in the laboratory. It's not often that you would have to convert anything from a US system to the metric system. But if it does arise, you have plenty of resources out there to help you with those conversions. But you could do it using the various methods of using ratio and proportions, or by multiplying it by whatever conversion factor is required, or multiplying it by whatever measurement the metric system requires for that conversion factor. So there have been a few revisions to the metric system, and the latest revision is to include the System International, which is the SI, or the International System of Units. And so what this done has kind of based it off 7 units to include length as meters, mass as kilograms, concentration as moles, time as seconds, electrical current as amps, temperature as kelvins, and light intensity as candela. Within the clinical laboratory, this change to the SI system primarily affects some of the chemistry laboratory results. And so these enzyme measurements were the first to use the SI system. And recent trends report that enzyme measurements in mass rather than activity. And so an example of this would be the MB, or the muscle brain fraction of the CK results, which results in the nanograms per milliliter versus units per liter. And so once we start getting into some of your chemistry analytes and stuff, you'll start seeing these measurements a little bit more. There are 3 different types of measurements used for measuring temperature, which include Fahrenheit, which most of us are familiar with, Celsius, and kelvins. Most of what you'll see while you're working in the laboratory will be Fahrenheit and Celsius. And so you do want to be familiar with, more particularly, the freezing points and boiling points, things like that. Because you will need to kind of be familiar with what is a normal temperature range for your freezers, your refrigerators, or any kind of procedure that you're doing. And so you will kind of need to be familiar with converting Fahrenheit and Celsius depending on what thermometer you're using and what it will measure. So you should be able to be familiar with how to convert from Celsius to Fahrenheit and from Fahrenheit to Celsius, because you never know what you might run across in the lab, and sometimes these are good registry certification questions as well. And so let's look at a couple of examples. So you do have equations that you can use to do these conversions. You've got 2 different equations here. And of course, if you were to convert the 9/5 over, you'd get 1.8. And if you were to convert the 5/9 over, you would get 0.555555556 because it rounds up. But for now, we're just going to take it out to 3 significant figures. So let's first talk about the temperature of 4 degrees Celsius. So this is what a lot of your refrigerators in the lab is considered kind of the temperature that you want to maintain within a couple of degrees, depending on what department you're in. But let's just say for blood bank, the storage units that you keep the units of blood in, the large refrigerators, has to be somewhere around 4 degrees Celsius. So you don't want it to go too low because it could freeze things, and you don't want it to go too high because it could cause those blood units to warm up and not be preserved. And so if we were going to kind of do that conversion of 4 degrees Celsius, and we plug that into this equation of 1.8 times the 4 degrees Celsius plus 32, and then we kind of simplify that down. So 4 degrees Celsius is equivalent to 39.2 Fahrenheit. And so we're all kind of familiar with 32 degrees Fahrenheit is freezing. And so we know that 39.2 is above that. And so that can kind of help you correlate to understand that that is above freezing. So that is about refrigerator temperature. Now, if we were going to kind of do the conversion the other way, let's think about body temperature. So we're all used to the 98.6. If we plug that into the equation, minus 32 times 0.556, I just took it out to 3 significant figures since that's what our 98.6 degrees is at. And when you do that math, 98.6 degrees Fahrenheit is equivalent to 37.0 degrees Celsius. And if you're in the blood bank world, 37 degrees is the temperature that we have the the fresh frozen plasma thawers at. So the water baths are set at 37 degrees Celsius for thawing fresh frozen plasma. So that is about body temperature. So anytime I go to do that, I make sure that it says it's about 37 degrees. So as I mentioned in a previous lecture, a lot of students will have a lot of confusion when it comes to doing dilutions, and that's because of the terminology that's been used over the years with dilutions versus ratios. So we know that a dilution is formed by an actual ratio of a sample volume to a total volume. So when we talk about a ratio, we talk about a 1 part to additional parts. So in this particular example, you've got 1 part of sample to 4 parts of diluent. Then when we talk about a dilution, we talk about it as a 1 and 4 parts. So it is a 1 in the total, but we know that that total actually includes that sample as well. So this is typically how we would say this when we were talking about these examples, but the problem is the terminology that most people use nowadays. If they tell you that they want you to do a 1 to 2 dilution, well, you would think of that to look like this, 1 to 2, which means that you would have 1 part sample to 2 parts diluent. But what they are actually referring to is a 1 to 2. So they actually want you to do 1 part to 2 parts total, which is actually a 1 to 1. So when we talk about this, when someone refers to you to do a dilution of a 1 to 2, they're actually referring to this as a dilution ratio. So it can get very confusing as far as what someone means when they actually refer to something as a 1 to an additional part. So you need to kind of be familiar with the different terminology and kind of understand when someone mentions doing a dilution, you want to make sure that you understand how to do it. But in the end, as long as you understand what an actual dilution is, that you're doing a 1 part and a total part, then you can kind of start to understand what to use of that dilution factor to actually get your calculations for that result. So now let's go a little bit deeper into dilutions and exactly what they are and what we use them for. So you may need to do dilutions depending on what department you're working in, but some of the examples of where you would use a dilution would be in the chemistry lab, where you might have a sample where that result is outside the linear range of that instrument. And so what we're talking about is the range in which the instrument itself has been validated to say that any result reported within this range and this range is considered accurate. So occasionally you might have something that goes above that range. So an example of this would be something like a beta HCG for a pregnancy test. So once those hormones start doubling about every 2.5 days, then you reach a point where that hormone level is outside of that measuring range of that instrument. So that would be an example of where you would need to do a dilution on the patient sample in order to get that value within a range in which the machine can measure. And then from there, you would do calculations to figure out what that result actually is. In the microbiology laboratory, we would do antibiotic dilutions, and this would be so that we could determine the MIC, or the minimal inhibitory concentration for the microorganism. So this is where you would do dilutions of the antibiotic to determine at which point does that concentration show that it is the lowest concentration that you would need of that antibiotic in order to prevent those organisms from continuing to grow and thrive. Within the immunology part of the laboratory, you may need to do serodilutions in order to determine the strength of the antibodies. When performing a dilution, we need to consider that there are actually 2 parts to that dilution, which includes the solute and the solvent. So our solute would actually be our sample or whatever we're diluting out. So this could be our patient sample, serum, plasma, or it could actually be like our antibiotics that we're doing a dilution on. And then of course we have the solvent, which is the diluent, and that is what we're using to actually perform the dilution. So sometimes this could be something like deionized water, or something like saline that you would actually use to do that dilution. or it could be some kind of diluent that is provided by the manufacturer. And so when we do that dilution, it's going to include the solutes, the sample, and the solvent or the diluent, and that's going to give you your total solution that you actually test. So when we do dilutions, there is a formula for it, and so that formula is sample volume over the total volume, which includes the sample plus the diluent, so you need to make sure that you remember that. And then when we talk about a dilution, as I mentioned earlier, it's often referred to as a 1 to 2 or 1 to 10 dilution. So when we mention it just like that, as I mentioned previously, you would think of that to be written out like this, when in fact it is actually written as a fraction. So if someone tells you do a 1 to 2 dilution on the sample, then they're actually meaning to do a 1/2 sample dilution. So just to kind of clarify it a little bit more, if we say a 1 to 10 dilution, then we're actually meaning a 1 to 10 fraction, or a 1 over 10, or a 1 part sample to the total of 10 parts, which means that we would have 1 part sample, and then we would have 9 parts of the diluent volume. So sample volume versus diluent volume. And so that's actually, would be written out as your ratio of a 1 to 9. So 1 part is sample, 9 parts diluent. But if we were actually to do like we had written out for a 1 to 10 ratio, then that's actually a 1 to 11 dilution. So now let's do a couple examples of some different dilutions, and trying to determine exactly what you need for your dilution. So in this particular example, we're going to do a 1 to 4 dilution of serum. And so when we talk about doing a 1 to 4, we're actually talking about a dilution ratio, which is 1 part of the sample to the 4 parts total. So we're actually doing a 1/4 fraction dilution. So we need to figure out how much we need if our sample volume minimum is 100 microliters. So you may have an analyzer that says that you need a minimum of this particular volume. So we need to try to figure out what that is. So we could plug that into an algebraic equation where we do 1 part of sample to 4 parts total. And we know that we need 100, so we can work the equation out this way. Our other option, we kind of know that one of the total parts is sample and the other is diluent. So if we have 100 parts total, we know that 1/4 of that is going to be our sample. So if you kind of can do some quick math in your head, you know that that's going to be, if you need 100 microliters, then 1/4 of that's actually going to be 25 microliters. However, when you work with some different numbers, you may not be able to do the math that easy. So if you plug it into the equation and then you do the cross multiplication, then that makes 1 times 100 equals 4x. So that gives you 100 equals 4x. And then, of course, you divide this by 4. And when you divide both sides by 4, that gives you 25, which is the same that we kind of figured out down here. So out of that total of 100, then you know that 25 of it is your patient sample volume. And so this will be your total. Okay, so now we'll do another example of a dilution. So let's say you have a dilution in which you add 0.5 parts of sample to 9.5 parts of diluent. And so what we're trying to figure out is what the value of the actual dilution is. So again, we got 0.5 of the sample with 9.5 of the diluent. So we know that that's a ratio, a 0.5 to 9.5 ratio. However, if we were to kind of figure it out in a dilution ratio, that we know that the total is going to include the sample as well as the diluent. So we know that that's going to give us a total of 10 once we add those together. So that would give us a dilution ratio of 0.5 to 10 parts total. Now, we could write that out as a 0.5 over 10, but you really don't do decimal points in a fraction because, a a decimal is actually a fraction in itself. But if we were kind of going to look at it in terms of an actual dilution, it'd be 0.5 over 10. So how to do the math for that to kind of simplify it a little bit will be, because we're dealing with a fraction, then we kind of need to bump that number up to a whole number. So in this scenario, we multiply it by 2 to give us 1. Well, of course, if we're multiplying this top number by 2, then we need to multiply that bottom number by 2 as well. So that's where this this right here comes in for your bottom number to actually be 20. So if we were to kind of write that out, then we would know that it would be a 1 over 20 dilution, whereas 1 part would be sample, and out of the whole of 20. After actually making your sample with a dilution with your part sample and your parts of your diluent, and you actually have that solution that you run on your analyzer, once you get that result, then you need to do something else with that result, because remember, you've diluted out that sample, so that value is only a fraction of what it should be. So what we do is we use the dilution factor, is what we term that number, which is the reciprocal of the dilution that you performed. So if we made a 1 in 4 dilution, or a 1 to 4 dilution ratio, and we ran our sample, so let's just take, for example, we do an HCG, because that's one that's diluted often, and we did a 1 in 4 dilution of that, and let's just say our result came out to be 1,000. That should be about in the analytical measurement range. Well, that 1,000 we know is only a fraction of that total result. So if we multiply that by our dilution factor of 4, then we know that that's going to give us a total result of 1,000, which is typically outside of our range of analytical measurement range on our analyzers for HCG. So here we have another example, a 1 to 5 dilution. So a 1 to 5 dilution ratio, which means it's 1 in 5 parts total, is to be analyzed. And our result that we got was 4.5. And so this was done on a creatinine. And that 4.5 now needs to be multiplied by our dilution factor. So what is our dilution factor? Well, our dilution factor is 5. And so when we multiply that out, we get 22.5 milligrams per deciliter. So we would report this out as 22.5 milligrams per deciliter and not the actual value that we got from that dilution. Now, a lot of your analyzers today will do dilutions for you, but if you ever have to do a manual dilution, you need to be sure that you factor in the fact that you did a dilution. So you either have to program it into the analyzer, or you have to manually perform that calculation and report it out. The dilutions that we've previously been talking about are just regular tube dilutions. And so you just have a different dilution for each tube that you do. So we just talked about like a 1 in 4 dilution, we talked about a 1 in 2 dilution, we talked about a variety of dilutions. So you basically just perform that dilution with your sample and your diluent on the one tube, and that is what your dilution factor is for that tube. Now, serial dilution is slightly different, because what this is, just like serial kind of indicates, it's a series of dilutions. And so you'll do the same dilution for each tube in a series. And so with this, you can do several different dilutions, but you only need just a small amount of serum or plasma of the patient sample to actually do that dilutions. And what you do is you start off with your tube number 1, in which you do your dilution. So you may start off with a half and half dilution. So maybe you do 1 part of plasma and 1 part of diluent. And then you'll take half of that and you'll bring it over to your second tube that already has half of your diluent. So you would go ahead and put diluent in all of these tubes. So let's just say the bottom half of all of these tubes are saline. And then each time you do a dilution, you would put your sample in here. So let's do a different color for our sample. So let's say we add the other part of sample, and we mix that up And then we take half of that and put it into the next tube. So each time we do this dilution, we've diluted it out by half. So the original sample volume that's in here is being diluted every time you go into a new tube. And so that's a serial dilution. In both cases, the final dilution is the product of each individual dilution. However, if you're doing a serial dilution, then each time you do that dilution, you need to be aware that you've got to multiply each dilution accordingly. Let's look at an example of a serial dilution. So for example, you want to make a dilution of some serum of 1 in 1,000. And so let's just say maybe again this is an HCG, or it could be something like an RPR test. There are plenty of tests out there where you can get some very high results, so you might have to do a higher dilution factor. So in this particular case, if we were thinking of 1 out of 1,000 dilution, then we could kind of look at, okay, simple things to use would be mLs, but that would be 1 ml out of a total of 1,000 mLs, which means 999 parts of that would be diluent. Well, that's a lot of diluent to waste. We don't really need to waste that diluent. So we could reduce that down. We could get our volumes to be 0.5 mLs or half of ml added to a total volume of 500 mLs, but that's still pretty big volume. So by doing a serial dilution, then we can do those dilutions in the tubes using smaller volumes of sample and diluent, and then eventually work our way down in the sequential order until we get the final dilution that we need of 1 to 1,000. Or excuse me, 1 in 1,000. So trying to work this example out in a serial dilution would look something similar to this. So we would start off with some smaller volumes. So first we would perform a 1 in 10 dilution of the serum. So to do that, we would take 10 microliters of the serum. So that would just be a very small amount of serum to the total part of the diluent, which would be 90 microliters, which will give us a total of 10 altogether. So out of that particular dilution in that first tube, then one part of it is sample and the other parts is the diluent to give you a total of 10. So this particular tube, our dilution factor is 10. So if we were to run this, whatever result we get, we need to multiply it by 10. Now we would take out 10 microliters, since we only added 10 microliters of sample into this first tube, we would take that out, add it to our second tube, mix that up, and then that would give us a 1 to 100, because now we only have a fraction of this sample has been pulled out and placed into this second tube. And so now if we were to run this tube on an analyzer and we got a result, we now have to multiply it by 100. And then we would proceed for 10 microliters come out of this tube, go into the next tube. So again, that's only a small fraction that's going to come out and go into this next tube. And then it's going to be reduced even more. So the actual sample that's in that tube is now at a fraction of 1 to 1,000. So our dilution factor is 1,000. So whatever result we get, we would have to multiply it by 1,000. So by doing a serial dilution, you can see that we've reduced our volume from, originally we were discussing possibly using 1 ml to 999 mLs to give us our total of 1,000 dilution. But instead we've kind of, by doing this serial dilution, we've reduced that down to where we really only need 10 microliters to start with. And then if we think about the 90 microliters of diluent in each of these tubes, then we've reduced that down to 270 microliters to get that 1 in 1,000 dilution. And so that makes your volumes that are required much lower, and it reduces the potential for waste. Now, occasionally you might run across a situation where you have to do individual tube dilutions. And so here for this example, even though you may not always do a dilution with this method, this kind of helps you understand the whole dilution process. But let's just say that you're running a test and it is over the analytical measurement range of that analyzer. So in this particular case, the concentration that is in the actual patient sample, so your original patient sample, would test out to be 1,650 milligrams per deciliter. But however, our analyzer will not read the concentration that high, so we do a dilution. So let's just say that our first dilution, we do a 1 in 5 dilution on tube number 1. So tube 1 has 1 part of sample volume, and then this bottom number will be diluent volume. But what we're going to do is after we make tube 1 and we run it, let's just say that the analyzer still gives us a result that is outside of the range. So we take that tube rather than making a new one, and we cut that tube in half. So we dilute it again. We take sample out of this diluted tube and put it in tube 2. And we run it, and it's still over the range, so we dilute it again. And this time we do it a 1 in 4. Still outside, so maybe we do a 1 in 5 this time off of this tube, tube number 3. Still outside, so maybe we have to do another one. And so we keep doing a dilution off of our original sample and just diluting it each time. And so what we want to try to do is figure out what is the calculation, or what is the actual concentration of the sample that is in each of those tubes. So first, let's figure out what tube number 1 is. So what we'll do is divide the first tube in the series by the dilution factor. So typically we would get our result and then multiply it, but we just want to know what is the concentration of that sample in tube number 1. So we kind of got to do a little backwards. So we'll take what the original is supposed to be, divide that by 5, which gives us 330 milligrams per deciliter, which would be what our concentration would be in this first tube alone. So then we'll proceed on. So remember tube number 1, we already got our value for that. So now we want to know what's in tube number 2. So once we cut tube number 2 in half, remember that was a dilution of 1 in 2 parts. So that gives us a dilution factor of 2. So we're going to divide that tube 1 volume, so this was tube number 1, not the volume, but the concentration of the sample. We're going to divide that by 2, which gives us 165 for tube number 2. So when we did the next dilution for tube 3, we did that 1 in 4, so a dilution factor of 4. We're going to divide our concentration of tube 2 by 4, which is going to give us 4125 for tube number 3. And of course, if we keep going, you see that we have to figure out what would our concentration be in tube number 5. So again, we're using that dilution factor of 5 and dividing it out with what was in the concentration in tube number 3. And so for tube number 4, we would get 8.25. So again, that dilution factor of 10 off of that last tube, divide that out, and so this will give us our final concentration that is in tube number 5. So performing titers in the laboratory is very similar to doing serial dilutions. And typically we're going to do these with any sort of immunology type test where we're trying to look at the quantity of an antibody that's present. So we might do a titer to find out at what point that particular antibody titers out. So a titer is the inverse of the dilution used in which a reaction occurred when testing an antigen-antibody type of reaction. So with doing titers, we will do a serial dilution of the patient's serum, and then we'll put those in individual tubes. So we'll again do that serial dilution. We'll have a series of tubes, and we'll take from one tube and go to the next. But each time you do it, you would do the same measurements each time. And so what we're looking for is whether or not we have a reaction in the tubes. And so once you do the dilution of the patient's sample into those tubes, then you're going to do something where you'll mix that sample or that dilution with some sort of antigen and see if you get some sort of reaction. So the dilution in which the last measurable reaction occurs is the actual dilution that you report out as part of your titer. So a low titer of a protective antibody may mean that the patient does not have immunity to a particular disease that you're testing for. But this is not the only time that we use titers. So there are a couple of different areas of the lab where we'll perform titers. So an example would be doing something like a rubella titer. So you want to look and see if the patient has immunity to rubella. So you could do a serial dilution of that patient's sample. And so each tube would just be lined up in a series. So you would put the same amount of diluent in each tube. So let's just say, for example, in this first tube, you used 1 microliter of sample volume. Which is actually a really small amount, but 1 microliter sample volume to 19 microliters of diluent. So each tube would have 19 microliters of diluent. So each time you go from one tube to the next, you would move or transfer 1 microliter. And so each time that you do that, you're going to dilute that sample even more and even more. And then something I want to point out that's not mentioned here, but typically that last tube that you dilute, whatever you take off, so that 1 microliter of sample, you would put it in this tube, and this would be considered a hold tube. So why would we do a hold tube? Well, if you end up doing your titer and you've still got reactivity in this last tube, then you have samples so that you could keep doing dilution should you need to. Some tests, depending on what it is, it would just stop and it would just say greater than 1,280 titer. However, let's just say, for example, you've made your titers for each of these, and you mix it with the antigen and you get reaction, but the last tube that you actually get a reaction in would be this 1 in 640. So this is the last tube here that we actually get a positive reaction in. So because that was the last tube, a positive reaction was found in all of these tubes, but this last tube, you actually got a negative reaction. So that means your last reactivity was here at the 640. And so we would report this titer out for this patient as 640 because that's the last reaction.